Okay, so now we're moving on to day 2, and in day 2 we're going to focus in on tests of significance specifically for proportions. Similar to what we did last unit, we're going to look at all tests of significance for proportions or percents, and then we'll look at all tests of significance for means in our next section, I guess I should say. So recall yesterday the basketball player who claimed to be an 80% free throw shooter. Remember that in his simple random sample of 50 free throws, he only made 32. And so his sample proportion, his p-hat value was 0.64, much lower than he claimed. So our job is to check to see if this provides convincing evidence against his claim. Is it statistically significant? So remember, we're using our hypotheses. The null HO says that P, our percent, is equal to 0.8. And that the alternate says that P is less, right? Our evidence based on our sample is less or lower than 0.8. Now, the 3 conditions for any test of significance match the 3 conditions for any confidence interval. So this is nothing new to us. We still have to have a random sample. We still have to have independent trials, meaning that N is less, than 10% of the population. And we still have to show that we fit to the normal sampling distribution, meaning that N times P is greater than or equal to 10, and N times 1 minus P is greater than or equal to 10. All right, so remember, when running the significance test, we always assume that the null hypothesis is true. So in this case, our mean and standard deviation for our sample proportion, the mean of all our samples, would be equal to P, the claimed value, so 0.8. And our standard deviation would be equal to P times 1 minus P over the square root of N. Okay, now that comes from our formula sheet. So if I go to our formula sheet, which is, well, I'll just work my way back. Sorry, everybody. This is algebra 2. Here. This guy, it's not over the square root of N, it's over N under a big square root, but that would be that guy. So while we're assuming P, we would use this for our mean, the claimed P value, and this for our standard deviation. Okay, so I'm going to jump back to our notes, edit this formula because I did it wrong. What I get for filming videos months in advance. So square root of P times 1 minus P over N. All right, so we know from the 3 conditions that our sampling distribution is normal. So we know that a sketch of this sampling distribution would have a middle value of that population claimed percent 0.8. And then the standard deviation would go out 3, down 3. Right, so here this was 0.8. This will be the square root of 0.8 times 1 minus 0.8 over 50 shots. Okay, so I'm punching that in my calculator. We get 0.05656, so 0.0566. Okay, and so we can go ahead and fill that in. So this would be 0.8566, 0.9132, and 0.9698. Right, and then if we go down, 0.8 minus 0.0566 would be 0.7434, 0.6868, and 0.6302. All right, and so what we observed, that sample percent of 64%, right? Yep, 64%. It's like right here. So it'd be this area of the curve we'd be looking at. Tiny, right? That's going to be a very small area. That makes it seem like what we watched happen is really unlikely. But we watched it happen, so it can't be that unlikely, right? And so, in order to try to prove the null hypothesis is wrong, we took our sample. And like we said, in our sample, they got 64%, which is far from that assumed 80. So, now we calculate what's called a test statistic. That test statistic is just a z-score. It just tells us how many standard deviations away from the mean that our data point would be. And so to find it, we do the statistic. So in this case, we'll say z, it's a z-score, is equal to our p-hat value minus our assumed parameter p divided by that standard deviation, p times 1 minus p over n. All right, now that's kind of on our formula sheet. So if you go up here, oopsies, it is right here, standardized test statistic minus parameter divided by the standard error. So you just have to know which bits and pieces from either this proportions table or this means table to use in order to use your formula sheet for this. Okay, so find the test statistic for this basketball player example. So we would say his data point is, 64%, minus the mean, which we said was 80%, divided by that standard deviation 0.566 that we found. So his z-score is negative 2.82 standard deviations below the mean. Pretty darn far below, right? When I highlighted this area, that was right about there. Okay, so now what do? That test statistic says how far the sample result is from the assumed null hypothesis value, which was 80%. So in this case, here is our sketch, right? We've got our 80% in the middle. We've got our standard deviations. This points out where that p-hat value is, and it gives us a p-value, right? Now if we jump over here, this is the standardized normal curve. Notice instead of all the 0.8 and then the standard deviations, we've got 0, 1, 2, and 3, negative 1, negative 2, and negative 3. That z-score we just found, this rounded a little differently than we did, with a p-value. So now let's talk about how we find that p-value, right? That p-value correlates with the alternate hypothesis. So it says the shaded area under the curve in A shows the p-value. B, over here, shows the corresponding area on the standard normal curve, which displays the distribution of our z-test statistic. So we are going to use normal CDF to find any p-value, right? So we would say normal CDF, because our alternate hypothesis was that p is less than 0.80, that tells me we shade our curve over to the left, right? So negative 1,000 to our test statistic, our z-score, negative 2.8, we found 2. And on the standard normal curve, that mean is 0, the standard deviation is 1. So if I punch that in my calculator, second vars, normal CDF, negative 2.82. Well, hang on, my calculators. Not cooperating. Okay, so that should give us that p-value of 0.0023. Okay, so hopefully you followed along with that. We are going to do another one though, so that should help if we need that help. All right, so if we move on, this sort of I guess, summarizes the things we just talked about. So if we look at, hang on, I'm resetting my calculator so that it works now. Okay, so if we look at this, it says to do a one sample z-test for proportions, we call it a z-test because it is a z-score that we use. We take a simple random sample of size n from a large population, so that n is still less than 10% of the population, that contains an unknown proportion p of successes. Remember, we don't know the population, we're just testing claims about it. To test our hypothesis, the null being that p equals some claim value, we use this formula for z, right? Remember, this, all come from your null hypothesis. That's the claimed p-value, whereas p hat, that guy, is from your sample, all right? Then we find our p-value using normal CDF. So we take our z-score and we shade either above if our alternate is greater, below if our alternate is less, and we'll actually shade on either side if it's not equal to. Okay, so let's do another example. You and your friend are playing a game of chance using a quarter. If you flip the coin, it lands on the head side, you win. If you flip the coin and it lands on the tail side, your friend wins. Out of 100 random flips, your friend gets 72, making him the winner. You claim that the coin must be weighted to land on tails, right? 72 out of 100 seems pretty far from the expected 50%. Does this scenario satisfy all three conditions for running a test of significance? So, did we take a random sample? Yes, 100 random flips. Is each trial independent? Well, yes, for sure, because flipping a coin is going to be independent, but also because 100 is less than 10% of all possible flips. Okay, and then normal. All right, in this case, to show normal, we would do p times 1 minus, oh my gosh, you guys, n times p. So 100, and in this case, we use the claimed percent, because remember, we're assuming it's true. So we're assuming 50%, so 50 flips would be each way. That's definitely greater than or equal to 10. And then 10 times 1 minus 50% is also 50, which is also greater than or equal to 10. So when you check for normal, we check to see is n times p and n times 1 minus p both greater than or equal to 10 using the claimed null hypothesis percent. Now the test statistic is going to say that z equals our sample percent, so p hat is 72%, 0.72, where p, our claimed percent, is 0.50. So 0.72 minus 0.50 over the square root of 0.5 times 1 minus 0.5 over 100. Okay, so here we get 22 over 0.05. So 4.4. So that means we're 4.4 standard deviations above the mean if 50% is actually the mean. So now to calculate that p-value, we're going to draw our normal curve centered at the assumed percent. Oh no, not centered at the assumed percent, centered at 0 because we standardized our score. So now 4.4 will be up here. And in this case, we are thinking for our null that p equals 0.5, and our alternate would say that p is weighted, so it's greater than 0.5. Because of that greater, we're going to shade our area to the right. So we put that into normal CDF and go from 4.4 to 1,000 with that center value of 0 and a standard deviation of 1. And we get 5.416 times 10 to the negative 6. So 0.1, 2, 3, 4, 5 zeros, 54. Tiny, tiny p-value, which again, remember from yesterday, small p-values help you disprove the claim in favor of the alternate. So in this case, we might be saying, yes, it is a weighted coin because it's really high compared to the 50%, and therefore we have a really low p-value. All right, so in your practice today, you will practice just these steps of calculating the test statistic, checking off the conditions, and finding the p-value. Tomorrow, we will do a full test of significance from start to finish.